for everyone wants to go home now, and after a long and day with a lot of talks, I would say we get started, or? So yeah, welcome to our talk about the combination of Apache Flink and Apache Mesos, so two Apache projects which actually work quite well together. And we, the presenters, that's Till from dataArtisans, and me, I'm Jörg from Mesosphere. So I represent the Mesos side, and you're the Flink representative here. Let's just understand the motivation for this endeavor. So why do we actually need something? Why do we need stream processing? Why do we need something like Mesos underneath? Back in the old days, computing was rather monolithic and rather simple. We had those big machines, and that was all we needed to operate. Nowadays, if we look at a typical data center, it looks a little more complex, and it is also a little more complex to handle and to keep this all up and running. So, and if we look on the application side, where at least as much has happened as in the data center itself, also we see that the patterns have changed quite a bit. About 5, maybe even longer, so 7, 8 years ago, the MapReduce was ruling the earth, and every company or companies were starting to build their own MapReduce cluster, because this was the first open source tool allowing them to actually process large data sets and to get value out of those data they were collecting. Nowadays, MapReduce isn't fast enough anymore, so we need something faster. MapReduce, it used to be this big batch processing, so we usually had something like days to hours of response time, and this in this modern world simply isn't enough anymore, or it's too long, taking too long. So if we look at modern architectures for this fast data processing, we see like a typical pattern. And this pattern, it's not necessarily about this individual technologies, it's more about the pipeline, how it's set up. And this pipeline is often described by the acronym SMAC stack. So SMAC in this case stands for, the S stands for Apache Spark, the M stands for Apache Mesos, the A stands for Akka, and the C stands for Cassandra, and the K actually stands for Kafka, because this was the first pattern of pipelines people were actually building for this kind of fast data processing. What I find more important than those specific technologies is actually this first row. So what is actually happening in the SMAC stack? We have some events coming in. This could be credit card data. This could be the Airbus example Ben mentioned this morning in his keynote. So any source streaming events and streaming data into my system. And with such kind of fast data pipelines, I want to decouple the producer, the event producer, from the actual analytics. So here I often have a queue, message queue, and the most commonly used one here is Apache Kafka, and we will also use Kafka later on in our presentation. If you haven't used Kafka, or if you haven't heard of Kafka yet, I like to describe it as like a big fire hose, so you can have named pipes connecting producers, data producers, event producers to event consumers. And so they're responsible then for bringing over and making sure this data gets delivered. Whatever happens. So it's also useful as a buffering system in cases you might have burst loads of events. So for example, when an Airbus A380 is landing, it produces like a lot of events, and your stream processing, your analytics pipeline tool might not necessarily be able to handle all this at once. And then actually this Kafka queue, this message queue, can also serve as a buffer to buffer those spikes and actually allow the analytics framework to catch up on this data. Next part, as already mentioned, is the analytics layer. So this is the actual work being done, the smart thing in the stack, which tries to get the value out of our data. Once we have found the value in our data, figured out interesting results, we also need to store them and persist them somewhere. And so there the storage part is becoming valuable. And of course, it all doesn't help us. We can store as much as we would like if we can't act up on this data, if we don't have any tool either representing it to user in some UI or actually doing decisions based on the outcome of our analytics. So this is what I would usually describe as this typical fast data pipeline here. And then if we look at especially the data analytics part, we see that there has happened an evolution, and this evolution doesn't necessarily mean that the old techniques, they get extinct, but we see a lot of those techniques being applied together. It started out with the MapReduce example where we had this typical batch processing, somewhere days to hours of response time. So this was really slow. It was okay if we did billing or if we did some big analytics end of the month, but for doing something more interactive, for example, product recommendations, it's simply too slow. And this is where actually Spark came in with its micro-batching, allowing us response time somewhere in the range of minutes to even some seconds. And so this is already sufficient if we want to do product recommendations as Amazon is doing it, or some real-time pricing and routing where you don't need an instantaneous but fast answer. Still, for many use cases, even this isn't enough. And I like to use the example of credit cards. So while I'm here in China, I'm using my credit card quite often. And my banks, they will actually check, oh, this credit card is being used in China. Is that an okay transaction? Is it really Jörg committing this transaction? So they need a really fast decision, whether it's a fraudulous event, a fraudulous credit card usage or not. And here, they don't want to wait for a second for the answer. Here, they actually need the answer in microseconds. So we need something faster, which can actually give us results in microseconds. And their Spark is simply, due to this micro-batching, too slow. And here, we actually come to the Flink part of our talk, because Flink actually enables us to have this event processing down in the microsecond range. And thereby, I would hand over to Till.
Thanks, Jörg, for the nice introduction. Before I get started with the actual content of my talk, I want to quickly say some words on behalf of my employer. So who are we and what are we doing? dataArtisans is the company which has been founded by the original creators of Apache Flink, and it is now dedicated to help developing Flink as part of the open source community. Moreover, dataArtisans develops the DA platform, which is at the moment a supported Flink distribution, but will soon contain some more useful tools for running Flink jobs. So, for those of you who have never heard about Flink, the best way these days to describe what Flink is that it offers stateful, event-driven, event-time-aware processing. So this might sound a bit abstract. So what you do to define a Flink program is you provide user functions which are run as part of a data flow. The operators which run the user functions are processed continuously. So whenever an event arrives, it is directly fed to a user function and processed. This user function can have some kind of state or memory, which makes it stateful. And this aspect allows you to implement quite complex behavior. And especially important when we talk about stream processing, where you have to deal with data which can potentially be out of order. Flink offers you support for event time, so to reorder the events, which is necessary to get the correct results out of a computation. And with these building blocks at your disposal, you can, on the one hand, you can build event-driven applications using paradigms like event sourcing or command query responsibility segregation. Or on the other hand, you can also do more traditional things like stream processing analytics, where you have a data stream on which you define windows, which you aggregate to generate some business intelligence, for example. Or like batch processing as well. That's probably what you know from MapReduce. How is this actually possible? So what's the key to Flink's versatility? The key is the common distributed streaming data flow runtime, which is used to run stream programs as well as batch programs. So you can also see that in the stack where the data stream and data set API are on the same level. On top of that, Flink also offers some libraries for higher level abstractions, like to do, for example, graph processing with Flink's Jelly library, or to do some machine learning with Flink ML, or complex event processing. But the important part here is that the runtime is shared, and that the streaming and batch are treated as first-class citizens. In the future, we hope that we can unify these two actually, because if you think about it, batch is actually in many senses a special case of streaming, just with the difference that you have finite streams which you are processing. Yeah. Okay. As I've mentioned before, you program Flink by specifying a data flow. A data flow always starts with a source, which generates some events. For example, reading data from a file on your disk, or from Kafka, or from Cassandra, and generating a data stream of these events. On this data stream, you can then apply computations, which can either be pure or can have state. So, for example, you could memorize what you've seen in the past, and depending on that, you change your behavior. So, a common use case would be that you have some kind of machine learning model which you use to do some classification, and at the same time you do online updates of this model. You can append multiple computations, combine them, and at the end, to output your results of your computation, you define a sink, which can can have different forms, like writing the data to disk again, or in some key value store, whatever you can imagine. So, if you now take a look at the API, how this looks like, is the following. So, first, what we have to do, we have to define our source from which to read the data. In this case, we do this, or we do this by calling the add_source API call on the stream execution environment, and give it a source function, which is a Kafka consumer. So we're reading from Kafka. Here we're reading simply strings, which gives us a data stream of strings. Let's assume these strings are the stringified version of some event, and we can pass an event from each line. And we can do this by applying a map transformation, taking the line and parsing it. And the result would be a data stream of events. Now we want to calculate some kind of aggregation on the stream, and we want to do this computations for each event. So first we key by the ID of an event, which basically partitions the stream into partitions which can be computed concurrently. For the aggregation, we define a time window of 5 seconds, and then apply our aggregation function, which calculates from a set of events a statistic object. And this statistic object is simply outputted by adding a sink, and here we're using the bucketing sink, which is a file output. So that's how you basically write Flink programs using the data stream API. So underneath, when you execute this program, a streaming data flow is generated, which has the form which you see at the bottom of the slide. So the first operator is the source operator, then it's followed by a map, followed by a key by window apply operator. So here we Flink chained multiple transformations to make it the execution more efficient. And then, last but not least, the sink. All right. now you've seen how you can generate a data flow, which we call a job graph internally, and that's happening on the client side. So to now see how the program is actually executed, we have this picture here. So what happens is after you generated the job graph, that the client, which is on the client side, of course, takes the job graph, connects to the job manager, which is the master of the Flink cluster, sends it the job graph, which is supposed to be executed. The job manager will translate this job graph into an execution graph, which is the parallel instantiation of this data flow, which means that every operator is now represented by parallel subtasks, which are then scheduled to the connected task managers. And this execution graph is also used for was mainly used for the distributed orchestration of the Flink job. And the task managers are then responsible for executing the actual code. So in the cluster setting, these are the workers. All right. So much for the execution part of Flink jobs. What you've seen is the data stream API. What you've also seen is that you need to be able to program Java or Scala at least. And for some users, this is not the right abstractions because many people like to think in terms of SQL. So Flink offers different levels of abstractions when you program it. So on the top level, the highest level is the stream SQL layer. So Flink allows you to write Flink programs by specifying a SQL statement. So it takes the SQL statement and generates a Flink program out of it, which is really nice, I think. Then one level below is this what we call the table API. The table API is integrated DSL into the Scala API, which allows you to program Flinks declaratively. It follows a bit the stream SQL syntax, and is a nice way if you want to combine the power of Scala, having access to lower level functionalities with a way to declaratively define Flink programs. Then we have the data stream API, which is the API which you usually use for stream analytics, where you have windows, or where you have streams and define windows on them and do your aggregations. And at the lowest level, to develop event-driven applications, there's the process function, which gives you access to individual events, their state, and timers, and is the latest addition actually. All right. That should be enough for a quick intro to Flink. Now you might ask yourself, what is all this good for? It's good for a lot, I can tell you, but let's take a look at some concrete examples to see what's possible. So Flink is used at ING, which is a Dutch bank, to do online fraud detection, so in real time. So what they do is ING processes credit card transactions, and they want to detect basically what Jörg mentioned at the beginning, what is a valid transaction, what is a fraudulent one. So they do this by having some machine learning models, which they train, and these models are constantly fed to Flink. Flink takes them and uses them to do classifications on the incoming credit card transactions. And yeah, depending on the result of this classification, it's either rejected or accepted. The important bit here is that all this processing has to be executed really, really fast, because so the latency has to be low, because a credit card transaction can only take so and so long until well, it is accepted or rejected. Flink is also used at Uber. They use it to build their Athena X platform on top of Flink. AthenaX is kind of a streaming SQL processing platform where you can use SQL to define some metrics. Additionally, you define some kind of thresholds for these metrics and actions which shall be triggered in case that a metric exceeds a certain threshold. And that is basically these rules read from like some store. It's a bit similar to the ING use case, and then Flink reads some incoming events from Hadoop, Kafka, or from some other store to run these elements against the SQL statements to generate some alerts which can be used by downstream systems. Then what Netflix does with Flink is, well, they have a simple use case. They use it for routing events between Kafka topics, Elasticsearch, and Hive, but also some more advanced use case where they try to sessionize well, user interactions with their app, and this involves some larger state. Additionally, they currently developing well, internally a system like a service, a stream processing as a service based on Flink, where they have their own DSL and some tooling around running these jobs, which can be used by the data scientists of Netflix to extract some business intelligence out of their data. Flink is also used at Alibaba. Well, to be more precise, it's Blink, a fork of Flink. They forked Flink a while ago because in order to run it at Alibaba scale, they had to do some improvements. And well, it's mainly used there for search. It powers some of their machine learning, things like recommendations, online feature updates, which ultimately leads to higher conversion rates on their website. But fortunate for Flink, for the project, Alibaba decided to well, join the team and contribute their changes back to the project. Such that they will, in the future, they want to switch back to the vanilla Flink version. And yeah, that's really great, actually. And last but not least, there's DriveTribe, which is a company which built a complete social network on top of Flink. It's DriveTribe. It's a social network for car lovers and petrol heads. But the interesting, like from our perspective, interesting thing is, well, that they didn't use Flink for analytics, but for building a complete application. So how this works is that Flink is responsible for maintaining the state of the social network. So for example, how many followers each tribe has, which is a kind of group in their social network, or which follower follows which other follower. So whenever you interact with a social network via the website, it generates a command, which is fed into Kafka, and Flink reads from Kafka, and sees, for example, that a follower now follows a new tribe, and it will internally change the state of this of the social network, write the state out to Redis and Elasticsearch, from which it is served again when looking up how many followers a tribe has. And this is all done with Flink, which is I think really awesome, to be honest. All right, so much for the use cases. Now let's take a look what all this has to do with Mesos. Well, as you've, I guess, figured out, Flink is a lot about computations and yeah, computing stuff. But at the end of the day, of course, you need some resources to run these computations. And there's where Mesos comes into play. I mean, there are different deployment modes. Historically, the oldest is a standalone mode where you run Flink on a bare metal cluster. But people like to use resource manager because they usually have many applications running on their cluster. For example, a Kafka cluster, some Hadoop and Flink, and using resource managers allows to share resources. Moreover, you can, it's easier to support dynamic scaling for these applications, and it's easier to realize features like high availability using a resource manager. And Mesos actually offers all the functionality we need to develop a fault-tolerant and elastic distributed application. which is a perfect fit for Flink. And interesting fun fact is that we did a survey among our Flink users back in September 2016. This was at a time when we didn't have proper Mesos support in Flink, and still 30% of the users were running Flink on Mesos, so they built it themselves because they were actively using it. So these are more or less the main reasons why we set out to develop a Mesos integration, which was first released with Flink 1.2. And most of this work was done by Aaron White. And it looks now the following way. And I see one arrow is a bit too short here, but it's okay. So the Flink framework consists of the following things. You have the Mesos App Master, which runs the Flink Mesos Resource Manager and the Job Manager. The Job Manager is responsible for running a job, and the Flink Mesos Resource Manager is responsible for talking to the Mesos Master. So it basically listens to resource offers and start Mesos tasks, which contain Flink's Task Manager. And once a Mesos task has been launched and a Task Manager has also been started, they will register at the Job Manager and are available for task execution. So the actual heavy lifting of this integration is done inside of the Flink Mesos Resource Manager. And let's now take a look at the components which we added to talk to Mesos. So inside of the Resource Manager, we have 4 components, which are the connection monitor, which basically monitors the connection to Mesos and tells Flink when it lost the connection. Then we have the launch coordinator, which receives the resource offers and processes them in combination with the task it is supposed to launch. And it basically does the matching between task and resource offers and the launching. Then we have the task monitor. The task monitor monitors started Mesos task and tells the Flink if things went wrong. For example, if a task was not properly launched after the launch coordinator told him so that it did. So in this case, the task monitor will trigger reconciliation. And it also makes sure that tasks, once Flink thinks a task has been released, gets properly killed. And last but not least, we have the reconciliation coordinator, which is basically responsible for syncing the states between Flink's resource manager and the Mesos masters with respect to the tasks it thinks it has running on Mesos. Okay, if we now take a look at how these components play together, we have the following picture. So the connection monitor, in order to say whether the Mesos master, whether the Flink framework is still connected to Mesos, listens to the status messages from Mesos. Then we have the launch coordinator. The resource manager tells the launch coordinator how many task managers in the context of Mesos, these are then tasks. The launch coordinator should start. The launch coordinator will then gather for some time resource offers and tries to do a matching between the tasks and the resource offers. Once this is done, it will basically tell Mesos which tasks launch where, and it will also tell the task monitor that some tasks have been launched. So the task monitor then listens to the status messages from the Mesos task, and in case, for example, if a message gets lost, so Mesos never learned about a launched task or a task to be launched, the task monitor will trigger reconciliation. This can also happen in case of a job manager or a master failover, where the resource manager retrieved the started tasks from a persistent store and now wants to check whether they're actually still running or not. Yeah. And one last slide for the launch coordinator. I said that the launch coordinator is responsible for the matching between the task and offered resources. In reality, we didn't implement it ourselves. We are using Fenzo for that. Fenzo is a general purpose task scheduler for Mesos frameworks developed by Netflix, and it has the nice feature that it is highly customizable. By being able to define like a custom fitness evaluator. This fitness evaluator basically allows you to optimize for certain constraints, for example, distributing the task equally among all hosts, or first maximize the CPU usage of on one host with your matching. And yes, that's basically it from the Flink side and the Flink integration with Mesos. I now hand over to Jörg again, who will tell you a bit about DCOS.
Let's just briefly go back to the data center, and I suppose most of us, we know about it. So just what we're seeing at this modern data center now with all those cool applications, the SMAC stack or the Flink stack we have deployed, we often see that it becomes a sub-partition cluster. So I take the first 5 nodes to install a Flink cluster there. I take the next 6 nodes to bring up my Kafka cluster there. Then another set of nodes for MySQL, and so on and so on. And this has 2 disadvantages. The first one being I have really a lot of manual operator overhead because I have to maintain those different subclusters over time. If there are node failures, I might have to shift resources if I want to grow a cluster, and so on and so on. Secondly, which is for most companies a bigger problem, is I'm wasting a lot of resources. I have to provision each of the subclusters for the maximum workload, so I'm actually wasting a lot of resources, and I end up with like a cluster utilization usually like around 15%, maybe 17, 20 if I'm good. And this is exactly the vision of Mesos, as we hopefully all know, or probably all know, is to treat an entire data center not as individual machines, but as like one big pool of resources. So I'm not saying I want to deploy Flink on those 5 nodes. I simply say I want to deploy Flink with 5 instances, and Mesos is taking care on which nodes that will actually happen. So I achieve much less manual operations overhead and also much less resource overhead because Mesos is treating us as one big pool of resources here. Why is Mesos so good for it? So I'm not going to dive into the Mesos architecture because it's hopefully was done by other talks, or you already know it, but the key point of it is that Mesos allows is a 2-level scheduling tool. So this 2-level scheduling tool, let me just jump back to one of Till's last slides, which is basically here. We can see here really nicely because Mesos is only concerned about the resource offer. So Mesos is offering some resources to the Flink scheduler. It will offer other resources to the Kafka scheduler, and so on and so on. And then it's actually up to the, in this case, the launch coordinator to decide which task does it want to launch. Do we want to launch a new job manager? Do we want to launch another task manager? So this is what we mean by 2-level scheduling, that Mesos itself can actually delegate that work to a framework-specific scheduler, because those schedulers, they look quite different for different frameworks. An HDFS scheduler is way different from a Flink scheduler, is way different from a Kafka scheduler. So this is why, at least in my opinion, Mesos is very well suited for this kind of problems because it allows me to create this user-defined functions, especially for startup and also failover scenarios, allowing me to recover from node failures. DCOS, so just for those of you who don't know DCOS, DCOS is an open source distribution built around Apache Mesos. So we've seen, or you also mentioned, like there are a lot of large companies using Mesos, Netflix, Twitter, Apple, they all have decently sized engineering teams dealing with that Mesos cluster. But most of us, we don't want to deal with it. We want an like out-of-box solution, giving me UI, giving me security, monitoring, and so on and so on. And this is basically what DCOS gives me and allows me to run all this big data on top. I can run microservices on top. So I don't have to have this manual operators overhead again to install a production-ready Mesos cluster. And this actually brings us to our demo. And the demo it's rather simple. We will create financial data. So you can consider that as like transactions. I will transfer money from account A to account B. This is written by the generator into a Kafka topic. This Kafka topic is consumed by Flink and then actually outputted again to Flink. So it's similar to the one use case you mentioned where also like Kafka is then used as the pipe and Flink is used as like the event driven tool to write my application in. So let me simply flip to my cluster. And this is one instance where I like other mics better. So this is the DCOS UI. And just the one sentence I usually like to say when seeing it, you see it's focused on resources. It's not focused on nodes. I have to scroll down to see the number of nodes because I, as an operator, if one of my node fails, I don't want to be woken up at 3 a.m. in the morning simply because of a node failure. I only want to be woken up if my CPU allocation is somewhere at 95% or my service health is going down because something is severely wrong in my cluster. And this is the focus also in the UI is representing that. So we have here the so-called universe. The universe you can imagine as the app store for your cluster. And being an open source tool, anyone can contribute. So we have a lot of community packages down here. And anyone who feels like his application should also be available on DCOS can simply come and submit a package here. But we care about Flink right now. So I can go in here and I can actually install Flink with a single click. And the second tool we need is actually Kafka. So let's also install Kafka. And there we have different versions, but I'm simply going to take the plain Kafka here. Okay, this is being installed. Let's have a short look at services. We see it's currently deploying. That means he's probably pulling in some resources right now, setting up the jobs, setting up the job manager in case of Flink, and getting everything started. While we are waiting for this to deploy, let's actually switch to the CLI, because we can also do a lot in DCOS using the CLI. And so we simply have here the DCOS command, giving us multiple options. If the network would be faster, it would also come up faster. And so, for example, we can use even DCOS Kafka topic list to list us the Kafka topics. So for those of you who might not know that, a topic in Kafka is this named pipe. So I can create multiple named pipes in which a consumer can write data and from which in which a producer can write data and from which a consumer can actually consume data. Okay, this looks good because that should actually mean Kafka is up and running. And I prepared a simple script because I don't want to type as much. And this will install the data generator and the individual topics. We'll have a look at this file in just a second. So now what we do, we create topics, so those named pipes for different cities. So this is the city of London, San Francisco, and this will represent the target of our transaction. So this is like I transfer money into an account in London, for example. Moscow, Tokyo. I don't think we have Beijing in here. We should change that next time for this demo. New York City coming up. And now we mentioned that we also have outputs. So Flink will output the results as well into a Kafka queue, and those are those Kafka queues being created here right now. So we have a dollar rate, we have a max dollar output, and we have a rate count. Great. So everything is deployed, and let's just have a short look at what we actually did here. So this is a simple script. And what it does in a loop, it does DCS Kafka topic create, and it creates all those topics we actually need. And then at the end, it will simply deploy, so it's the last line here, the DCS marathon app add generator JSON, which is like our data generator, and the implementation is actually a simple Go program. Okay, great. Have a look at the UI, whether everything is up and running. Yes, our generator is up and running. This is good. And this means we can actually start deploying our Flink job. So I'm going to the Flink UI. In production use cases, I would do that using the endpoints, but in a demo, it's actually nice to use the UI because it's a pretty neat UI. So I pick here my jar file with a job, and I upload my jar file. This is actually okay. When I ran it this morning, it took longer due to the network. And once I've uploaded that file, I can actually use it to run jobs also from the UI, which is a neat feature if you just want to play with Flink. So it made testing the integration quite simple. Great. So this is uploaded, and now we want to submit a new job. Let me just copy the parameters I need. So this is the entry class, read from Kafka, and now we have some arguments which I will explain in a second. So the arguments are basically which job we want to run, and in this instance we want to calculate like our fixture's dollar rate. We have a period which is like the window size of 10 seconds, and then we need to specify which our Kafka host is. The neat thing about DCOS is that it has inbuilt service discovery, so I don't actually have to look up on which node my Kafka broker is running. I simply have this concept of a named virtual IP, it's called. So Kafka has registered all its brokers. So if we look at DCOS, we will actually see that Kafka has deployed 3 brokers, 0, 1, and 2. And I can load, in a load balance fashion, reference all those brokers with this simple named virtual IP. Great. So let's submit that job and see what happens. So we can see here's a job and see the plan, what's actually happening. We can have a short look, should here appear under running jobs. Great, everything looks good. And let's have a simple look whether we can actually see the output coming out. So I started a simple Docker container here, which has the Kafka console consumer. So from here, we'll simply use this. This is a standard tool deployed with Kafka or Kafka tool. And so we'll simply read the Kafka dollar rate, in which Flink will actually output those results. And we see here, we actually have outputs. And we see every 10 seconds, whenever this window size is over, we are redeploying and getting new dollar rate here. So this was quite easy to set up. And by that, we set up a complete, not a complete SMAC stack, but a considerable subpart of our SMAC stack. And yeah, that actually brings us to our conclusion. So Flink runs pretty nicely on Mesos, and it's a really nice match because Mesos is taking care of this abstraction cluster management, and Flink can actually concentrate on what it does best, like which task it wants to start where, and then how to do the analytics. there's the DCOS Flink package, so it makes it really easy to install. You don't have to worry about what you have to deploy. It's a simple click, as we all saw. And for this package, contributions are actually very welcome. We'll have, end of this month, June 29th, a DCOS office hour, where both Till and I, we are looking for new contributors to both the package and also the Flink Mesos integration. So if that's something you care about, just join this office hour, or simply write us a short email stating that you're interested. That actually, thank you very much for listening, and this gives us almost no time for questions. Still, if there's like one question, I think we can still take it, or? Yes, thumbs up. No questions? Then thank you very much for listening, and would be nice to see some of you in the DCOS office hour also contributing to this project. Thank you.